Children, I hope you have gone through my previous videos and done all the work that was assigned to you. Let us now proceed further. Children, today we are going to start a new chapter, coordination compounds. It is a very important chapter from the examination point of view. A number of questions are asked from this chapter in the board exam. Now, coordination compounds. Before that, we should first study about molecular or addition compounds. When solutions containing two or more salts in simple molecular proportions are allowed to evaporate, crystals of new compounds called molecular or addition compounds separate out. And these compounds, they are of two categories. First category is double salts and the second category is coordination compounds. Now, if we see double salts, they are those molecular compounds which exist only in crystal lattice but break down into their constituent compounds when dissolved in water or any other solvent. Like for example, FeSO4 NH4 whole twice SO4.6H2O. This is also called as Moore's salt. So when you dissolve it in a solvent, it will separate into FeSO4 and NH4 whole twice SO4. Similarly, K2SO4.Al2SO4 whole thrice .24H2O. This is the formula of potash alum. So this is also a double salt, and on dissolving in solvent, it will separate into K2SO4 and Al2SO4 whole thrice. Second type of compounds are called as coordination compounds. Now, coordination compounds, they are molecular compounds which retain their identity even when dissolved in water or any other solvent, and their properties are completely different from those of the constituents. Like for example, CONH3 whole 6 Cl3 and K4FeCN6, etc. So K4FeCN6 does not have any of the properties like potassium or iron or cyanide. It has different properties from all three. Similarly, CONH3 whole 6 Cl3, it is unique in its own kind. So these complexes in which the ions do not dissociate in solution because they are quite stable, they are also known as perfect or penetrating complexes. Alright, and there are some complexes in which the complex ion dissociates to a appreciable extent and is unstable. They are known as imperfect complexes like K2CdCN4. In that, the potassium part can be separated. So that is a imperfect coordination complex. Now, before we study about these complexes in detail, there are some important terms which are used in coordination compounds with which you should be familiar, because these terms will be used again and again, and if you don't know the meaning, then you will not be able to understand. First of this is central metal atom or ion. Now, the metal atom or ion to which certain atoms or group of atoms are permanently attached in a coordination compound is known as central metal atom or ion. Like if you see the example K4FeCN6. Now, in this, 6 CN molecules are attached to iron metal. So, in this case, Fe is the central metal ion. Alright, they act as Lewis acid, and the oxidation state of Fe, which iron exists as ferrous and ferric. So in this K4FeCN6, it is Fe3 plus. That is the central metal ion, and it acts as Lewis base. Similarly, here if you see CONH3 whole 6 Cl3, in this case CO, sorry, this should be small letter, cobalt is the central metal ion. Now we come to second term, that is ligands. A ligand is a species that is capable of donating electron pair to central metal or metal ion. Now because it is donating electron pair, it is Lewis base. Ligand attaches to central metal through coordinate bond. Like in this case, CONH3 whole 6 Cl3. NH3 is the ligand. Same way in K4FeCN6, Cn is the ligand. Okay. Now classification of ligands. Ligands are classified on the basis of number of electron pairs it donates to metal ion, as well as on the basis of charge they have on the metal ion. So first let us see about the classification of ligands depending on number of coordination sites, that is the number of electron pair donated. First type is monodentate. Mono means one. So obviously it is donating one electron pair. Example of these are NH3. Nitrogen has one electron, one lone pair of electrons. Similarly PH3, phosphorus has one lone pair. H2O, oxygen. It donates, although oxygen has two lone pairs, but at times it donates only one electron pair. So it forms one coordinate bond, it will come under monodentate. Cn minus, carbon has one lone pair. N3 minus, OH minus, NO2, CO, all these are examples of monodentate ligands. Second category is bidentate. Bi means two. So here the ligands, they are donating two electron pairs, two donor atoms, and they form two coordinate bonds with central metal atom or ion. Example, see here, oxalate ion, C double bond O, O, C double bond O, O, 2 minus. This is oxalate. Similarly here, CH2NH2, CH2NH2. This is ethylene diamine. In short, it is known as EN. Now both the nitrogen have one lone pair, which it is donating. So this is also a bidentate ligand. Another is CH3C double bond N OH, CH3C double bond N O. So again two nitrogen, both having one lone pair each. This is dimethyl glyoxymato, DMG. Next category is of tridentate ligands. They have three donor atoms and they can form three coordinate bonds with central metal or ion. For example, NH2, CH2, CH2, NH, CH2, CH2, NH2. Now in this diethylene triamine, it is known as diene, D-I-E-N, diene. So in this case, there are three nitrogen atoms present, and all three, each nitrogen atom has a lone pair which can be donated to form the coordinate bond. So it can donate three lone pairs and form three coordinate bonds. So it is known as tridentate ligand. Similarly, there is tetradentate ligand. As the name is telling, tetra means four. So a compound which is capable of donating four lone pairs, which has four atoms which can donate a pair of electron for coordinate bond. See, NH2, CH2, CH2, NH, CH2, CH2, NH, CH2, CH2, NH. This is called triethylene tetraamine. Triene. The previous one was diethylene, so diene. This is triethylene, so triene, short form. Okay. Here there are four nitrogen, 1, 2, 3 and 4, and each is capable of donating a pair of electron to form coordinate bond. So it is a tetradentate ligand. Next comes pentadentate ligand. They contain 5 donor for atoms. For example, ethylene diamine triacetate acetato, it should be ion. This, see, ethylene diamine is NHCH2CH2N, and to this 3 acetate ions are added, CH3COO, CH3COO, CH3COO minus. So there are 3 acetate ions attached to ethylene diamine. So this is ethylene diamine triacetate ion. Similarly, for hexadentate, to ethylene diamine, 4 acetate ions are present. See, N, CH2, CH2N. This is ethylene diamine. And to this, instead of hydrogen, there are 4 CH3COO minus attached. Like this. So this becomes ethylene diamine tetraacetate ion. In short, it is called as EDTA. Many times in the exam, it is asked what is the full form of EDTA. So ethylene diamine tetraacetate ion, and you should remember the formula of this. Next type of ligands is bridging ligand. Bridging ligands, they are monodentate ligands which can simultaneously attach themselves to more than one metal ion. For example, OH minus, NH2 minus, CO, etc. Okay. Now, all the ligands which you have studied just now, which have more than 2 donor atoms present in the molecule, that means tridentate, tetradentate, pentadentate, hexadentate, they are all also called as polydentate ligands. Now next is classification of ligands depending on nature of charge on ligands. This is very simple. First is neutral ligands. They do not have any charge on them. They are neutral. For example, water, it is called H2O is called aqua. NH3, it is called amine. CO, it is called carbonyl. NO, nitrosyl. C2H5N, pyridine, etc. Second category is anionic ligands. They have negative charge like F minus, fluoro, Cl minus, chloro, Br minus, bromo, Cn minus, cyano, OH minus, hydroxo, and so on. CH3CO minus, acetato. See, all the anionic ligands, they will end with O. Then next is cationic ligands. They carry positive charge like NO plus. It is nitrosonium ion. NH3, NH2 plus, hydrazinium ion. NO2 plus is nitronium ion, and so on. Okay. Next we come to chelation and denticity. Some ligands, they are capable of chelation and denticity. Some, before that, okay, we'll do that later on, but just now you have studied about chelation and denticity. Some ligands, they are capable of, let me see, where did it go? Yeah, here it is. Donating more than a single electron pair from different atoms in the ligand and to different sites in geometric structure of a complex. They are called as multidentate ligands. When bonding of a multidentate ligand to a metal ion produces a ring which is of 5 or 6 members, then such complex is called as chelate, and the process is known as chelation. Number of such ligating groups indicates the denticity of the ligand. Chelating ligands form more stable complexes than unidentate ligands, and this is called chelating effect. In general, chelating ligands which do not contain unsaturated groups, you know what is unsaturated groups? Double bond. They form 5-membered stable rings. Chelating ligands which contain unsaturated groups form 6-membered stable rings. Example of chelating ligand, see, this is the central atom Cu, and this is the ligand NH2, CH2, CH2, NH2, but it is forming 2 coordinate bonds here, and similarly over here also. So this is forming a ringed structure having 5 members. So it is called as a chelate. Next is flexidentate character or polydentate character. Some of the coordinating sites of polydentate ligands may remain free as they do not form coordinate bond with the central metal. For example, SO4 2- is a bidentate ligand, but in some complexes it acts as monodentate ligand. It forms only one coordinate bond. Okay, because only one negatively charged oxygen ion forms coordinate bond with the metal ion, and it acts as unidentate ligand. So it is flexible. So this is called as flexidentate character. If it wants, it can form 2 coordinate bonds, or it can form only one. Next is ambidentate ligands. Now ambidentate, the monodentate ligand which can coordinate with central metal atom through more than one site, is called as ambidentate. Like see over here, NO2. Now in this case nitrogen also has lone pair and oxygen also has lone pair. So there can be a condition where nitrogen is forming a coordinate bond with the metal, central metal, or there can be another, that is, such compounds are called as nitro compounds. And there can be another condition in which oxygen forms a coordinate bond with the central metal, then they are called as nitrides. Next is coordination entity or complex ion. Now coordination entity, it contains a central metal atom which is bonded to a fixed number of oppositely charged ions or neutral molecule. It also represents the coordination sphere. The part of complex behaves as one unit and it cannot be ionized. For example, CONH3Cl3. This is a coordination entity. Okay. Now a positively charged complex ion or coordination entity, it is known as cationic complex, like CONH3 3+. This is a cationic coordination entity. Similarly, a complex which has a net negative charge, it is called as anionic complex, like AgCN2-. And a coordination entity which does not have any charge, it is called as neutral complex, like NiCO4. There will be no charge on it. PTNH3 Cl2. These are the neutral coordination entities. Now next is coordination number. Total number of coordinate bonds which are formed by the central metal by the ligands, or the total number of ligands which are attached to central metal, it is called as coordination number of that ion. Like let us see a few examples. In AgCN2, coordination number of Ag plus is 2 because 2 cyano molecules are attached to it. Similarly, CONH3 Cl3, coordination number of CO3+, oxidation state is 3+, but how many ligands are attached? 3 NH3 and 3 Cl3. So the total coordination number is 6. Similarly, FeC2O4 3, coordination number of Fe3+ is 6. Okay. Why is that? You will wonder now, because there are only C2O4 is 3 only, but I am saying that coordination number is 6. This is because C2O4 oxalate, it is a bidentate ligand, and each oxalate molecule that should be counted as 2. So 3 into 2, 6. Next is oxidation number or state of the central metal atom. Now It is an electric charge which the central metal has or appears to have when bonded to other ligands. Oxidation number of neutral ligand is 0. Oxidation number of negative ligand is equal to the charge on the ligand. Like in case of Cl minus, it will be -1. Oxidation number of cation will be equal to the charge on the cation, like K plus. Oxidation number will be +1. Oxidation number of central metal atom has to be calculated. Okay, now let us see. Like if you want to calculate oxidation number of nickel in NiCO4. So oxidation number of nickel plus 4 into oxidation number of CO, because 4 CO are attached to it. And this overall molecule is neutral, so it should be equal to 0. So oxidation of nickel into 4 into CO, carbon and oxygen. Carbon monoxide, it is neutral, so that is 0. So oxidation number of nickel plus 4 into 0 is equal to 0. So it will become 0. So in this case, oxidation number of nickel is 0. But if you look at oxidation number of Fe in K4 FeCN6. Now in K4 FeCN6, 4 potassium are there. So 4 into oxidation number of K plus. What is the oxidation number of potassium? 1. 4 into 1 plus oxidation number of Fe plus 6 into oxidation number of Cn minus. Oxidation number of Cn minus is what? -1. So 4 plus oxidation number of Fe minus 6 is equal to 0. So oxidation number of Fe will come to what? +2. In this way you can calculate the oxidation number of central metal atom. Now next is coordination polyhedron. Now coordination polyhedron, it is the spatial arrangement of ligand atom which are directly attached to the central atom. For example, if you look at CONH3 whole 4 Cl, CONH3 whole 6 3 minus 3 plus, it has octahedral symmetry. NiCO4 has tetrahedral symmetry. Why? Because 4 ligands are attached, so tetrahedral. CONH3 6 3 plus 6 ligands are attached. So when 6 are attached, the symmetry becomes octahedral. Now similarly in CONH3 whole 4 Cl2 Cl, the different terms are shown below. Here this CONH3 whole 4 Cl2, which is given between big bracket, whatever is given between big bracket, it is coordination entity. In this, whichever metal is present, that becomes the central metal ion. The remaining, they become the ligands. Alright, coordination number is 4 into 2 plus 4. That becomes 6. Alright. And what is given outside, that becomes ionizable or counter ion. Okay. Now next term is homoleptic complexes. Complexes in which central metal atom is bonded only to one type of ligand, it is called as homoleptic. Homo means same. Like see here, CrNH3 whole 6. 6 ligands are there, but all of them are same type, NH3. Heteroleptic, hetero means different. So a complex in which different type of ligands are there. For example, COEN2Br2 plus. Now in this case, 2 ligands are En and 2 are Br. So 2 different types of ligands are there. So the complex becomes heteroleptic. Now next term is effective atomic number. Effective atomic number or EAN of a metal ion in a complex, it is given by atomic number of metal minus oxidation state of metal ion plus 2 into coordination number. This is the formula. EAN is equal to Z minus oxidation number plus 2 into coordination number. A stable complex is formed if EAN is equal to the atomic number of the nearest noble gas. This rule is applicable in many cases, but in some cases it fails. Okay, so that is all for now. The remaining we will do in our next video.